And you're okay to go to 3, right? About half an hour, right? Well, that's okay?
Yeah.
Okay.
Should be fine.
Let's see. Wacht even, dat is 3. 3 was er in me. I see. Okay, let's start. So, great pleasure to have Dr. Will Hicks amongst us here, who is at our Center for Quantum Social and Cognitive Science at my university back in Newfoundland, at Memorial University. Will did his PhD under supervision of Dr. Marco Merkli in Mats and Andreas Bukas, who is linked to the, the Volterra Center at the University of Torino, I think. And has done a lot of work, Will has done a lot of work on open systems and has applied them also on financial, in financial contexts. And Will, the floor is yours. Now, Will is going to have to disappear from the screen because his internet is not very good.
Yeah.
So, okay, Will,
yeah.
floor is yours. So.
So thanks for the organisers for the invite. I really appreciate it. It's an absolute pleasure. There's a little bit of a delay, so it's slightly disconcerting. So hopefully it works out. I'm going to turn my camera off now to give myself the best chance of getting through it without too many delays. So, okay, so I'm going to give a talk today on applying open quantum systems to the modeling of the financial markets. So there's a slight delay in the slides, unfortunately. So the general idea is that if we have enough data, so if we're looking to price a particular asset, so this can be an equity that we are looking to purchase on the stock market, and if we know enough about, for example, exactly what the future cash flows of the asset in question will be, then we can calculate a pretty accurate price for how much we should pay for that asset. And really, when we turn to things like stochastic processes, probability, in my view, it is because a lack of information. So whether that is down to information regarding the market and regarding what's going to happen, so good news, bad news, etc. And the real power of the open quantum systems approach is to do with the fact, the flexibility in terms of modeling, if you like, the decay of the value of the information you have. Much more flexible approach than classical stochastic calculus. Okay, there's a little bit of a delay. It's really confusing. Okay, so the first point I wanted to make is that when we look at, when we use classical stochastic processes, generally we talk about volatility. Okay, now in actual fact, both volatility and entropy are strictly increasing in time. So if I have a classical stochastic process, if I determine one, I really determine the other. So whilst we talk about, if you like, the variance of our probability increasing as we look further and further into the future, I think partly what we're saying is, in actual fact, the information value of what we currently know is decaying. So I think this concept of information entropy is important. So then what I wanted to do with this slide is to talk about a simple toy example of why really in the quantum world, as I'm sure you're familiar, you're sort of breaking the link between variance and entropy. So they're no longer both monotonic, and knowing the variance, monotonic in time, you can have a unitary process where your variance increases without entropy moving away from zero. So in the quantum world, you're sort of breaking the link between the two. So the example here is if we have 3 possible price outcomes, so it might be high, medium, and low, okay? and we have a listed stop price. So we have eigenvectors E1 for low, E2 for medium, E3 for the high, and associated prices X1, X2, X3. And at the same time, we say we can do a straddle option on the same stock. The straddle option has a low valuation if the stock price is in the middle, so E2 eigenvector, and then we know it pays out a little bit more in if the stock price is either high or low. And we say that the market can attach two different values. So it can give a high value to your straddle option, which would be, in my notation here, O2 plus, and it can have a low valuation to your straddle option, and that would be O1 plus. Okay, so we're now going to consider two different quantum states. The first quantum state is just a diagonal density matrix. So this is what I would refer to as a classical density matrix, simply because you're saying 25% chance you have a low price, 50% chance you have a middle price, 25% chance you have a high price. The second quantum state we're going to consider is still 50% chance we have a middle price, but then we say there's a 50% chance of finding ourselves in the V1 eigenvector, one of the eigenvectors for your straddle option. Now, crucially, both these quantum states have the same classical probabilities. They both will, if you trade a listed stock, you still have 25% chance low, 25% chance high, 50% chance in the middle. But in the second case, the market has eliminated the possibility of the high valuation for the option. So this would be, if you like, a market that didn't like the straddle option. And this additional piece of information is reflected in the lower entropy. Okay, so some basic background, which I'm sure everyone is familiar with. In the classical world, we have the Shannon entropy, which is just minus the sum of P log P. If we are in a discrete model with n different outcomes, then the maximum entropy case is just 1 over n, so log n. In the quantum world, again, basic stuff. We have projection operators onto each possible eigenstate, and then the classical probabilities are retrieved by taking trace of the density matrix acting on your projection operator. And then in the quantum case, we have the von Neumann entropy, and if we are in a diagonal density matrix, what I refer to as classical density matrix, then the Shannon entropy and your von Neumann entropy are the same. So I think it's an important result, but I mean, I think it's fairly standard, well known, but I think it's important, is that if we look at the set of density matrices which fix the classical probabilities, so all the density matrices in your set all agree on P1, P2, and so on, then it's actually the classical density matrix which maximizes the von Neumann entropy. So whenever you have something, a non-diagonal density matrix, it means that there'll be a lower von Neumann entropy and your state contains some additional information. Now, of course, if you're in a pure density matrix with entropy 0, then there'll be some contract which has a fixed price. Even in reality, that might be something completely non-tradable, but nonetheless. Okay. So just to go through some background on the open quantum systems approach now, again, many people will be familiar with this. The basic idea is you have Hilbert space for the markets, Hilbert space for the environment. And in my case, I consider the environment made up of a discrete space representing different levels of risk appetite. So you'll have an eigenvector representing the market at its most bearish, risk-averse state, and then another eigenvector, EK, if you like, representing the most bullish, highest risk appetite. And then you attach a space of square integrable functions, which essentially, it's partly pragmatic because you need some kind of continuous space for everything to converge. But I mean, you can think of it as being the amount of energy you need to flick between the different risk appetite states. Okay, so just a quick word on the Hamiltonian now. So we have an interaction Hamiltonian, which we'll speak about in a moment. We have a Hamiltonian acting on the environment, which I'll speak about in a moment. But just to make the point here that we use a zero Hamiltonian for the market. Now, I could use my market Hamiltonian to give my wave function a constant drift. I could use it to model some kind of, I can use it to model some kind of complex market structure. But the focus on my talk today is on the the decay of the information value. So the sort of what a classical stochastic process would think of as random diffusion. Okay, so that's the focus. So to simplify everything for the time being, we assume that we have a zero Hamiltonian. Okay, so in terms of the interaction, pretty simple. We have an operator B up that shifts the environment to a higher risk appetite, and the resulting impact on the price A up, and then we have B down and the associated impact to the price A down. So you might say, in a simple case, you might say B up being high risk appetite, A up being price jumps up, and similarly more risk averse, so bad economic news, and then the price jumps down. Okay, I'll skip over that slide. Okay, so the general idea is that the operators we're interested in execute a trade on the market, right? So we don't gain any information regarding what's going on in the environment. So the state we're really interested in is the so-called reduced density matrix. So we take the reduced density matrix, we take the partial trace over the environment state. Okay, and then to get the master equation, we just start with our standard von Neumann equation with a second order expansion, plug in our partial trace, and we end up with a master equation that looks something like this. So first thing to say about this is, in general, it's non-Markovian, and again, one can argue back and forth about whether you want your model for your financial market to be Markovian. Just to simplify things for the time being, we assume a Markovian model. So there are two ways in open quantum systems world in which you can achieve this. Again, fairly basic stuff. You have the weak coupling limits and the strong coupling limits. Now, partially for financial reasons and partially for pragmatic reasons, we assume the strong coupling limit in this case. But the important point from all of this is we end up with a Markovian equation that looks something like equation 17. Okay, so the first term at the top is a drift term, so we can safely ignore that, and that will be zero in most cases anyway. The sigma squared term will, if you use A up, jump up one in price, A down, jump down one in price, then the sigma squared term will just be a discretization of a standard diffusion operator. So this will give you just a straightforward Gaussian process, okay? And then crucially, if you have a diagonal environment state, then that's all you have. So you'll just end up with a straightforward Gaussian diffusion. If you have a non-diagonal environment state, then you get the additional quantum terms below. So nu up, nu down, and we'll see what these guys do in the coming slides, the impact they have on the diffusion. Okay. So just to emphasize what I mean by a classical system. So if we have a diagonal observable, so a matrix, just a diagonal matrix for my observable, and I have a diagonal density matrix, and I apply a standard Gaussian diffusion, then my density matrix will remain diagonal, and I essentially have a classical model, right? I have a sort of quantum representation of a essentially classical model, and the expectation is just x1 times p1, x2 times p2, and so on. Okay. But I can, of course, use non-diagonal operators. So if I want to have an illiquid, let's say a particularly large trade or something with non-standard contract terms, I can use a non-diagonal matrix. If I want to represent an imperfect market mechanism, I can use a non-commutative state, non-commutative density matrix. Okay. So the key thing I wanted to talk about today is thinking about what the sort of long-term behavior of these of this process, and what happens to the entropy, and characterizing different orbits for the diffusion. And in order to do that, it's the easiest way to proceed is to put your diffusion process. So equation 17 you can write in standard form. So equation 18 is really the bread and butter standard form for time for master equations in open quantum systems world, where you have L1 and L2. And if L1 and L2 are orthogonal, then we have what I term a classical diffusion. Okay, so you can think of good news equals price jumps up, bad news, and then price jumps down. But you can, of course, if you have a quantum diffusion, then L1 and L2 have they're no longer orthogonal, and you could have up or down in either event. Maybe there's a small chance that the market shifts down even though you've had good news. Okay, so just a key result here. So two things to say on this slide. The first thing to say is that if I have orthogonal operators, so L1, L2 are orthogonal, so we either have price up or price down, and we start out with a diagonal density matrix, then it remains diagonal forever. And all you have is the probability mass flattening out along the main matrix diagonal. The second important point I wanted to make on this slide is that the diagonal sums are unaffected, but unaffected by the diffusion process. Okay, so clearly the main diagonal sum is just the trace, so that stays at 1. But if you take the diagonal sum immediately above the main diagonal, immediately below, and so on, these diagonal sums are constants over the whole diffusion process. Okay, so that enables you to think about what happens to these diffusions over the long term. So crucially, if I start out with a diagonal density matrix, then eventually it won't stay diagonal, but it will eventually end up diagonal. In the long-term limits, if I start out with a diagonal density matrix, a classical density matrix, if I start out in a classical system, regardless of my choice, whether I have quantum diffusion or classical diffusion, I'll end up back at the maximum entropy state. Okay, if I have non-zero elements, and if my diagonal sums are not 0 to start off with, then actually turns out that the long-term entropy limit is determined by the so-called turplets matrices. So these are matrices with constants along each of the diagonals. And in actual fact, the entropy you finally reach, the maximum entropy you finally reach, is fully determined by your initial density matrix. Okay, just to show what happens now in a classical diffusion. So what I've shown here is an example of where you have oscillations in the matrix elements immediately above the main diagonal. Okay, now all I'm showing, so you start out with a big sharp oscillation at t0, and then you apply your classical diffusion, and then, if you like, it's not probability mass, but the matrix, the non-zero in the non-zeros in your matrix elements above the main diagonal just diffuse away. So they just flatten over time. Okay, so all the probability mass moves diagonally, basically, or the non-zero elements in the density matrix moves diagonally. Okay, so what's happening in your non-classical diffusion? So what I show here is a made-up density matrix on the left. Okay, so this is a classical density matrix, a roughly Gaussian diagonal classical density matrix. So we know all of the diagonal sums remain at 0. But if I apply non-classical diffusion, then I start to get oscillations in the matrix elements immediately above and immediately below the main diagonal. Okay, so because I started out in a diagonal state, in actual fact, I will eventually reach my maximum entropy state. But if I apply non-classical diffusion, it will take me a lot longer to get there. Okay, so I just wanted to briefly talk about observables now before we move on. So
another 10 minutes, right, Will?
Yeah. Sorry, it's a bit of a delay. Yeah, okay. So, this is really frustrating. Okay, so if we have a classical observable in a diagonal operator, then I can think of that as being something like a listed stock price, if you like. Or if I'm trading the major indices, then there's a lot of liquidity in a listed futures. So right now it might be the DEC 2025 listed future. So if we have let's say we have a density matrix which has fixed the price for our DEC 2025 listed future, then I might still have some variance in my March 2026 listed future. So, I mean, this is where I can start to think about what do I actually mean by the non-diagonal operators. Okay. Now, if I feed everything into an expectation functional with my density matrix and my operator, I can rotate everything around. I can rotate all the operators around, and I can quite easily, rather than working in a sort of Schrodinger-like interpretation where all the time evolution goes into my density matrix, I can rotate all of the operators within my trace, and I can come up with a Kolmogorov backward equation, okay, where it's actually the, if I have a non-classical diffusion, it will actually be the operators that become non-diagonal. But importantly, one or other of the, so if I start out diagonal, okay, one or other of the density matrix will remain diagonal and the operator becomes non-diagonal, or vice versa. Okay, so if you like, I can consider that I apply my Lindblad master equation approach, and I can my diagonal operator remains diagonal, and I put all of the non-classical diffusion onto my my density matrix, but it doesn't really matter, right? Because I have a diagonal matrix for my observable, so the probabilities will be read off the elements in the main diagonal, right? So the off diagonal elements definitely impact the time evolution, but they don't impact the probabilities. And the point I wanted to make on this slide is, if you have both non-diagonal operator and non-diagonal density matrix in the basis that is fixed by what you consider to be price up, price down, then you end up with, you can no longer easily extract the classical probabilities in the density matrix, and now the off-diagonal elements actually impact things. Okay, so I wanted to show some simulation results. I don't have too much time left. So the simulation I've set up, you'll have to apologize. There's a delay, which is really frustrating. The simulation I've set up is we start in so I have 101 different the 101 different prices. I've said -1 to +1, so you can think of this as log price or something like that. Time steps roughly akin to 1 day, sigma of 0.4. And we start out in a diagonal density matrix, okay? And there are two things that I want to track. I want to track the ratio of the von Neumann entropy over the classical entropy, okay? So 1 minus that, simply so if you have 0, it's a purely classical density matrix. If it goes up to 1, it's a purely quantum density matrix. And then the second metric I wanted to track is your sum of squares of your elements immediately above the main diagonal. So the simulation we undertake, we start out with 5,000 5,000 time steps of non-classical diffusion, and then we switch. We have between simulation one, where
Yeah, Will, you're breaking up quite a lot.
classical,
Yeah, Will, you're breaking up quite a lot. So
simulation one, I then carry on 95,000 more steps of non-cyclical, and simulation two, I switch over from my entropy based. In the non-classical diffusion, your entropy based metric on the non-classical side carry on increasing for quite a long time.
Will, you're breaking up quite a lot. Will, do you hear us?
Both of these guys will eventually hit the maximum entropy. You started out in a diagonal matrix, so both of these guys up in the maximum state, but the non-classical diffusion is going to take a lot.
Okay. Will, I don't know. Did you see the message? You're breaking up a lot, Will. I don't know.
You can see on the excess kurtosis slide, you
oh my God.
can see that as you apply the non-classical diffusion, you end up with a non-Gaussian probability distribution, which gives you that. And then you can see
it's
right.
Yeah. Okay. Will, I think it's completely broke up now. I see Will is asking us if there are any questions, but he's on a different planet, right? He's beaming from Mars. So there's a bit of a delay there. Okay.
Again, both of these.
Okay.
Guys.
Wait. One moment.